Okay. Now, got a satellite in a circular path of radius r, constant velocity around a planet. We got Newton's law of universal gravitation. And we want to know how the velocity is related to the distance from the planet. Now I should probably have an r here. I'm using r for the radius, okay? So there's our situation. What do we know? We know that it's moving in a circle, the satellite is moving in a circle at a constant speed. We know that if you're moving on a circle at constant speed, you need centripetal acceleration, v squared over r, which means you need centripetal force equal to m times v squared over r. The only thing you got out here in an isolated system with a planet and a satellite, the only thing you got to exert a force on anything is gravitation. So the gravitational force is what gives you the centripetal acceleration. And the gravitational force, g times big M little m over r squared, has to equal the centripetal force. Solve that for v, you get v equals square root of g m over r. G times big M over r. So we know the speed this thing has to have to be in a circular orbit. You give it more speed, well, take it out of the circular orbit and go into some kind of an ellipse, okay? You slow it down, it goes into a smaller ellipse, hopefully not so small it hits the planet. Although if you're trying to get back home, okay, you do want to get close enough that the air slows you down without burning you up so that you can dissipate all that kinetic energy and see green fields again. Okay. Now the potential energy relative to infinity, that's equal and opposite to the work done by gravity. Gravity being your conservative force as you go from r to infinity. Okay, so it's integral from 0 to infinity of f grav times delta s. Okay, and we're going to assume a straight line path straight away from the planet. We do it for more general spirals and stuff like that, but we don't want to invoke that mathematics. It kind of gets into molecular calculus. Okay, so this is the work done by the conservative force. This is the negative of the work done by the conservative force, which is the change in potential energy from r to infinity. Now, if you measure potential energy relative to infinity, that means what's the potential energy change from here to infinity, okay? And we get a simple integral using x for the axis along which I move to infinity. Very simple integral. And our derivative of x squared is negative 1 over x, giving you big G, big M, little m over r when you substitute the limits in. And you can work through the details of that. Very simple. If you substitute infinity for x, you got an x in the denominator, you get 0. Okay, you don't really substitute, you take the limit as x goes to infinity. You substitute r for x, you get this. This is your lower. Do I have something screwed up here? I think I do. Yep. Too many negative signs, I wrote it down backwards. I thought about it when I did that. I thought, no, the signs come out right, I must have done that right, I didn't. Okay. So, anyhow, this does come out negative big G, big M, little m over r. That's your potential energy relative to infinity. Okay? Well, I've got my limits in that right or not. This is okay? I don't want to stop and think through that right now. I think I did something backwards there. Kinetic energy is 1/2 mv squared. Well, V is this. Square it, you get big G, big M over R. Multiply it by 1/2 little m, you get this. And this is half as big as this. Okay? But this is negative. Your total energy is therefore the sum of the potential and kinetic energies, negative 1/2 big G big M, big M little m over R. Okay? Now, we want to talk about the change in total energy from circular orbit at R1 to circular orbit at R2. What's the change? Well, it's going to be this quantity evaluated at R2 minus the same quantity evaluated at R1, which means you're going to subtract the quantity at R1 from the quantity at R2. The quantity at R1 is negative. Well, both quantities are negative, so subtracting the quantity at R1, you're going to get a plus 1 over R1 essentially, and you can work through the algebra of that. It's very simple, just write it down. Negative 1/2 big G big M little m over R2 minus negative 1/2 big G big M little m over R1. The one with the R1 is going to end up positive. And that makes sense because to get from a lower orbit to a higher orbit, you've got to go to a greater energy. It takes energy to get from here to here. Okay? And of course, if R1 is smaller than R2, then the reciprocal of R1 is bigger than the reciprocal of R2, and you're going to get a positive change in energy. Now, you probably want to listen to this and work that out because we talked about it more in length. Now, let's say we're in an orbit at R1 and we want to get to an orbit at R2. Okay? Now, if we add a kinetic energy equal to this, okay, and an impulse, okay, we got this thing going around here, we give it a quick burn, and we increase its speed, it's going to go out to an elliptical orbit. It's going to come back to this point, and we work through the geometry of that, but nobody knows enough geometry to do that, so we're not going to. I mean, nobody comes out of our educational system at this point knows enough geometry to talk about this. I won't say nobody, 0.1% maybe, and only maybe 0.2% have even seen it. Okay. It's horrible. Okay, so we have an impulse here, takes us out there. If we add this, we're going to find the new velocity at this point. Well, the velocity at R2 turns out to be too great. Okay? So this is not how we get from this orbit to this one. Okay? You figure out why I say the velocity would be too great. But it has to do with the change in total energy. Okay? This change in total energy involves both the change in potential and the change in kinetic energy. Okay? So anyhow, an impulse here would lead us to an elliptical orbit. If we use the right impulse, we get out to the right point. If we use too much impulse, we go too far. We just want to get out to R2. This is not what we do. It's some kind of symbol. If we then want to get into a circular orbit out at this distance, then we tweak it again. So we do another impulse. Of appropriate size, takes us out into a circle. It would be kind of an orbit transfer. Now orbital transfers get really complicated, especially when you got more than two bodies. If you're trying to get from here to Mars, you got to worry about the sun, you got to worry about Jupiter. Otherwise, you know, as long as you put in your mass in kilograms and not in pounds, which isn't even a unit of mass, maybe you hit Mars. If not, a few $1 billion in 1990s money down the drain, and that happened. Okay? I don't know how many heads rolled for that. Probably not the person that put it in. Probably the supervisor didn't check it. Okay? Should have redundant checks on the data.
Yeah.
and redundancy fell apart there. So, okay. Now, if they paid back the $3 billion, they might get their job back. Or maybe they got demoted, humiliated, I don't know. Don't know what their culture is. Okay, anyhow, you get the idea? Okay, these things get put together to answer that question.